How's it going, everybody? And welcome back to our Cisco Enterprise series, where we're going to be focusing on continuing the Switched Campus series. We're going to be talking about spanning tree protocol, at least a high-level overview of how that works and all that. So we want to dive into what the purpose of spanning tree protocol is, or STP. So spanning tree, span tree, I've heard all different iterations of it. Essentially, spanning tree's job is to detect loops at layer 2 in the network and put in a blocker or a cop, if you will, on a particular port that could be used as a loop in the network. So the best way to describe this would be if you look at gig 00 on switch 1 and 2, and you look at gig 01 on switch 1 and 2, you notice that when you have links like this would be a perfect use case for a loop. Where if I sent a spanning tree message, also known as a BPDU or a Bridge Protocol Data Unit, that would leave switch 2 on gig 0/0, be received by switch 1 on gig 0/0, then be sent back out gig 0/1 from switch 1, and received in on gig 0/1 on switch 2. If that was to be the case, that would continue. And the reason why that would continue is because the way that spanning tree operates is that every 2 seconds on a per trunk link interface, on a per VLAN basis, you send a hello. Every 2 seconds on every trunk link for every VLAN. You do this consistently so that you will always know how the network is built. If there is an issue somewhere in the network, you will be able to identify it, and then spanning tree will be able to recalculate. I say that with air quotes because there is a recalculation process that comes into play. And there are 3 different modes for spanning tree. We'll talk about that in a moment. So how does spanning tree go about preventing a loop? Well, the simple answer to that is we end up having a blocking of a port. So one of these interfaces, in this particular case, switch 1 is my root bridge, which is the center of the universe for a layer 2 environment. What would end up happening is he would send BPDUs out both of his interfaces towards switch 2, and switch 2 would do the exact same thing. So what would end up happening is switch 1 would learn about switch 2's environment, switch 2 would learn about switch 1's environment. And so what would end up happening is switch 1 would be considered the root bridge, and because switch 1 would be considered the root bridge, then one of these 2 interfaces, gig 00 or gig 01 on switch 2, would need to be elected the root port. The root port is the lowest numerical port on the switch that would point or is downstream of the root bridge. Any interfaces on a current switch that is not the root bridge that would be used to connect to the root bridge, which is logically south of the root but it points to the root, would be considered the designated port. The designated port would then be identified as the root port. Designated ports are on the root bridge, so I correct myself there. So the root port on switch 2 would be gig 0/0 because it's the lowest numerical interface, and then gig 0/1 would be blocked because of the fact that it's the next interface up. The same thing would happen with switch 4. You'd end up having gig 00 on both switch 3 and switch 4 would both be considered the root port because they both point to switch 1, and gig 01 on both switches would be considered the blocking port because they would both be blocked in order to prevent any type of connectivity from happening. Now there's going to be alternate ports and stuff like that. We're going to get into that more in detail later. I'm not trying to articulate how spanning tree at an in-depth level works in this particular video. So we have 3 different modes of spanning tree. We have PBST plus, Rapid PBST plus, and MST. PBST plus, or per VLAN spanning tree plus, is the first iteration. So that would be your IEEE 802.1d iteration. And it has some variables attached to it. So you would have a a listening, a learning, and a forwarding process. There's also a blocking and a disabled if you want to really get technical. And what I would definitely recommend you guys doing, if you really want to get into the weeds of how spanning tree protocol works, is pull up Google and type in understanding rapid spanning tree. And then you'll be redirected to this document right here, which will go through. This is spanning tree protocol. This is going to, this is going to walk you through troubleshooting tech notes. If you wanted to come back to spanning tree protocol, you could understand and configure spanning tree on catalyst switches. You could come to here, and it's going to walk you through how spanning tree works and all the details that go along with it. Now, this is an older document, as you can see in some of the model switches that are out there, but at the end of the day, it works similarly to the way that everything else works. So I definitely would recommend that you guys all read through this documentation. And this isn't this is CatOS, by the way, with the way that the output, this is CatOS. So actually, I take that back. Let me move you over to, so go to your favorite web browser, and I'm going to go to Google and spanning tree protocol. So just type in spanning tree protocol, and then bring this guy over. I'm going to go ahead and put him in, and then you're going to, and I'll Cisco, and then you are going to want to look at, actually I take that back. The best way to go about doing this would be to, let me go ahead and get out of the way so you guys can see this better, is go to Cisco's website, close these two out, and what you're going to do is you're going to look for the products and services. You're going to click here. You're going to go down to networking. You're going to go to all networking products. They've changed this up a little bit. It looks a little bit different than last time. Access networking. So this will be like layer 2 networking. And we are looking for switching. Explore the Catalyst 9000 switches. So we're going to come down to here. And I haven't seen this in a while, but explore the 9200 switches. And there should be, I'm letting it load. Let's see here. Documentation is not where I'm wanting to find it. Oh, I'm sorry. Support. View all product support. Here we go. This is better. Switches. We're gonna go to switches. Then we're gonna come down here to, we'll go to the 9000 series, Catalyst 9300. This is usually a pretty good place to go. And then we'll come down to documentation, and we are looking for the configuration. Yeah, configuration. So the configuration, this is a pretty good one right here. The software configuration guide for this particular version of code. This might be, I have to go back here a little bit and find a different version. Configuration. Let's see here. Is this the one I want? Yeah, I'm looking for, I need to go down to an older model. Something that's got a little bit more meat to it. Let's go down to 1610. Contents. Okay. So this will be a little bit more involved. So you'll be able to click on layer 2. And then you'll be able to come down here to spanning tree protocol. And then if you expand this out, and you'll have the ability of reading through all the different stuff that you can do with spanning tree. This is what I really want you guys to read through, is definitely be reading the configuration guides for all this type of stuff, so it'll break it down for you. If you read through all of this, this is a really good place to dive into the technology, understand how it all works. and that type of stuff. So I'm not going to go too deep into how spanning the differences between PBST plus, rapid PBST, and MST work. I'll just give you a high level overview of what they each do. So regular spanning tree is it's very, very slow. So you would have 20 seconds. It's 15 seconds of listening, 15 seconds of learning, and 20 seconds of max age. So you'd have a total of 50 seconds of timers for PBST when there's ever a reconvergence in the network. So this makes PBST pretty slow. To optimize PBST, they created rapid PBST, which works identically to the way PBST does in terms of the hellos and the BPDUs being sent and all that type of stuff every 2 seconds out every trunk link for every VLAN. The only difference is with rapid PBST, what you end up getting is instead of a timer-based value or timer-based mechanism for it to determine the environment, it uses a proposal and agreement where every switch in the network is queried to figure out who's connected to who and how, and then once it's been determined how everything is put together, then you can flip it over go through a negotiation process, which is much, much faster than timers. So on average, when you look at a environment where you've got a lot of switches and you are looking for fast convergence, rapid spanning tree is where you want to go. And if you had a lot of VLANs, which I don't really recommend you do, if you had, let's say, more than, I'll pick a number out of the top of my head. If you had more than 50 VLANs in your environment, I would suggest moving over to multiple spanning tree, where multiple spanning tree is going to dive in and allow you to send a single BPDU with a list of VLANs attached to it. So the idea is trying to optimize the spanning tree process in your environment. So that's a key thing that I really want you to understand is MST leverages rapid spanning tree for convergence, but optimizes it by sending a single BPDU with like a database of VLANs in its updates. Instead of every VLAN sending a BPDU every 2 seconds as a hello on every trunk link, you're going to send a single hello for all VLANs. And there's an unpacking process. It's loosely similar to the way BGP works with unpacking routes and stuff like that. Not entirely the same process, but there's a similarity to it in that respect. So that is the best, probably one of the better ways I could explain how MST works. So again, it goes back to if you want to know more about how MST works, you can dive into it. So the best way to hear is based on the 802.1s. This is the W version is MST, where you can map multiple VLANs to the same spanning tree instance, which reduces the number of spanning tree instances required to support a large number of VLANs. It runs on top of rapid spanning tree, which provides rapid convergence of the spanning tree by eliminating forward delay and by quickly transitioning root ports and designated ports to the forwarding state. So this is the type of information I want you guys to read through because it goes into the really the meatier chunks of how spanning tree works. Now, you might ask, well, how come you're not going into a ton of detail? Like, is it, well, what's the deal with that? And the simple answer to that question is this. Once you understand the basics to spanning tree, you're never going to go into anything really complicated. So those of you that are planning on taking this series as to the nth degree, meaning you're going to use it for preparing for your CCIE, then by all means, get into the minutia, dig into it. But for this, for the CCNA and the CCNP candidates out there that are just looking to have a better understanding how spanning tree works, this is really what my this course is really geared to, is to that. I'm not really trying to dig into the minutia of understanding the frame formats and understanding all the MAC addresses and all the type of stuff that goes along with that. If you want to know that information, by all means dive into it. That is not what I'm trying to convey here, because I don't want to have a YouTube video that's 2 hours long that dives into how spanning tree works in intricate detail, because I'll get like it won't be the bang won't be worth the buck for me. It's not worth my effort to go through that level of detail. So, but for the average person that wants just a quick review of how spanning tree works, this is essentially what I'm trying to do. So, you might wonder. I used to wonder when I first started with spanning tree. I was like, okay, well, how do you determine the root switch? Who's the root bridge? A bridge and a switch are essentially the same device. They're layer 2 devices. And now a bridge from the olden days, which meant like early 2000s and before, were different than a switch. A switch came in and provides a level of what's the best way to put this? Gives you more functionality than you would get if you had just a bridge in place. Where, with a bridge, you're all in one broadcast domain and one collision domain. Well, with a switch, you can have multiple broadcast domains, and every interface is a collision domain. And you'll get into carrier sense multiple access, collision detection, collision avoidance, and all that type of stuff. And I'll talk about that more when we get into like switch management and things like that, because there's a piece to that you really need, you do need to understand and stuff like that. But I'm gonna throw it out there that it's not a super finicky topic that I needed to cover right this moment. So if you wanted to change who the root bridge in your environment is, you would use the switch priority to do that, which is a numeric value which ties with the bridge ID, which is going to be the base MAC address of the switch, and the VLAN ID, which is known as the extended system ID. You couple the bridge ID together, so the MAC and the VLAN ID. You combine those two together. They don't literally become one. It's two pieces of information that become one piece of information. So the base MAC address plus the VLAN ID, or the system ID extension, which is the VLAN ID. So you couple MAC and system ID extension, that value. You couple those together with the priority value, because you can't manipulate the MAC address or the system ID extension, because when you create a VLAN, the system ID extension is already added to it, and the priority. So the priority, the VLAN ID gets added to which is the system ID extension. The system ID extension, the VLAN, gets added to the priority, which by default is 32768. So you add the VLAN ID number, the value, 10, 20, 30, 40, to 32768. That gives you your priority. And you take the MAC address, you take those two pieces of information, and then when you take that information, that is your bridge ID. That is disseminated to all other switches in the environment that are still at layer 2. So if you only have one switch, you only have one bridge ID. If you have two switches, you have two bridge IDs. So you take the priority with the system ID extension built into it, or added to it, I should say, and the base MAC address. You take that information, that becomes your bridge ID. You send that to everybody else in the network. The base MAC address is going to be used as a determining factor initially when spanning tree protocol converges. So what you would do is, once spanning tree has figured out who the current root bridge is, once that information has been determined, then if you want to adjust who the root bridge is, you have to go to an individual switch that is not currently the root bridge, but you want to become the root, and you need to lower the priority value in increments of 4096. 4096 is the number you need to type in increments of that. And then by lowering the priority value to something lower than 32768 plus whatever the system ID extension is, once you've lowered that value by 4096, that will change for that particular VLAN which particular root bridge for that VLAN is. So it's not a switch level configuration. It's done globally on the switch, but you can do it per VLAN, which is why it's called PVST. So the switch priority is modified to affect which particular switch is going to be the root bridge for which particular VLAN. And the reason I say it that way is because if I have switch 1 and I have switch 2, I could have switch 1 the root bridge for all odd VLANs and switch 2 the root bridge for all even VLANs. And I can keep doing this over and over and over again. It makes it very, very easy to figure out who's doing what. So if I wanted to make that adjustment, I could. And that is what we'll be talking about, that and how that would come into play. Beyond that, we have the port priority. Now the port priority by default is you have 128, and then you have another value. Let me pull up switch 1 real quick and show you what I mean here. If you do a show spanning tree, right, you have this 128 and a dot. You can go ahead here and you can affect that. So if I was to go to interface gig0/0 and type in the spanning tree port dash priority, and come in here, and you can affect the port priority in increments of 32. So for example, if I was to put in here and say, let's say 32, and do show spanning tree, you notice how the number went down to 32, right? So what I could do is I could use that to affect downstream traffic. So I'm on gig0/0, and if I wanted to affect the other switch on a particular interface, I could do that. Now switch 2, it's not going to show anything, show spanning tree. So you notice that gig0/1 is alternate or blocking. We mentioned that a minute ago, that we knew gig0/1 would be alternate or blocking because of that value. Now that didn't have anything to do with the change I made here, but as you can see, the value is there. So I could go to, I believe it is, if I was to say no here, and go to here, I believe this is how you would change that. There's a capability in here. Oh, okay. Notice how that's changing? Notice how I changed the uplink interface. I went from gig, it was before, where it was alternate and blocking, but because I changed the port priority on gig0/1 by do show span to 32.2, switch 2 is now looking at that and going, oh, okay, so now gig0/1 is the root port and gig0/0 is the alternate port. And I'll come back to that, and I just wanted to show you what that looked like. It's very, very rarely will you ever make this kind of a change. This is one of those more intricate details where if you know how it works, and I seriously have not tested that in probably 10 years. I remember many, many years ago when I first discovered that you could do that, and when I was studying for the lab still, and I was actually a change was needed somewhere, and I made the suggestion to do that, and people across the table were like, you can do that? And I was like, yeah, you can change the port priority. And that's what they mean by port priority. So you can also tune the path cost. So you can change the cost value for spanning tree on a per link basis. So you notice how it says cost of 4 here, right? So I can go, I think I can do it on this side here too, is I can come in here and I could say spanning tree cost is 10 and do show span. Now I'm at 10. I think it'll bump this to 14. I honestly don't remember if that's how that works or not. I had to play with that one, but as you can see, by changing the port priority, this guy here, it changed the that value. I don't think it's going to affect it that way. So I don't think that's how it works. But I can change the cost value. You know what? Take that back. It's locally significant. So if I wanted to affect, if if I wanted to change on a per uplink basis, I could adjust the cost and then flip it around, but no one really does that. So the reality of it is, as long as you know, and feel free to test any of these capabilities out. I'm not trying to discourage you from doing that, but you can tune the port path cost. So for example, if I'm on switch 4 here, and my root port is gig 0/0 to switch 1, and I want to adjust that because it goes based off of cost. So if I was to bump this interface to be way higher, gig 0/1 should theoretically be my next root port. So let's actually take a quick look at that. So if switch 4, because I know my root bridge is going to be show spanning tree, I know my root is going to be for VLAN 1, this guy happens to be the root, which is kind of funny. So if I go back to switch 1, and for VLAN 1, this is the root. How is that? Is, beg your pardon? Show spanning tree. Huh. Okay. I might have to reset something here because this is not right. Switch 1 should be this value. So if switch 4, I'm actually a little surprised. Let me write mem here and let me reload. I'm just my goal was not to sit here and try to walk you through configuration, but sometimes it's like it makes more sense to do that. So the idea here is to make the cost, if this is the best based off the cost, and that's how spanning tree figures out how far away something is based off the cost value, and a cost is associated to the link speed. So for example, 100 meg interfaces would be a cost of 100, or sorry, a cost of 12, I think. So you'd end up having something like that happen, where you could bump up gig 0/0 to be the root port, and I might have to go back and make a quick adjustment. Like it's okay. This is not a hardware-based switch, so I might have to stop it and then restart it. Let me start the switch now. I wasn't planning on doing this, but let's see if this makes a difference. So the idea is to make the cost on gig 0/0 higher numerically, so the gig 0/1 is taken. And that's how you would adjust the environment. But then again, this is a virtual environment. So, okay, now that that's done, and it's signed off on, so show spanning tree, this bridges the root. Okay, 32769. So let me go ahead and make a quick adjustment here. Type in spanning tree VLAN 1, and I'm going to type in here the root, and I'm going to say primary. I'll talk about that here in just a second. Root primary. So now switch 4 should now learn that. Oh, you know why? My bad. The reason why this isn't working, show interface trunk. We have trunks. Trunking is configured. That's right, I already did that. So I'm like, why is this not triggering? This is very, very weird. I don't understand. Show spanning tree VLAN 1315. Okay, that's better. So I'm not sure why spanning tree wasn't showing up for that one, but we see how the idea is on here. We see that gig 0/0 is the root port, and gig 0/1 is the alternate port. If we were to go to interface gig 0/0 and type in spanning tree, cost is going to be 20, and do show span for VLAN 1315. Notice how gig 0/0 is immediately went to blocking, and then gig 0/1 is going to root and listening. So by bumping the path cost, the call on the spanning tree cost on a per interface basis up, you're changing which interface is going to be the better path to go. So now that that's forwarding, now gig 0/1 through switch 2 would be your better cost. So you can logically change the way that spanning tree figures out the directionality in the environment. So, and like literally this first video, I've shown you how to manipulate just about everything there is for spanning tree. So I'll go back to it again and we'll do some more demos and stuff like that. But this is basically what I wanted you guys to understand. So, but spanning tree is one of those technologies that I actually like to be on the CLI when I'm discussing it, because then it lets you guys see what's going on. So there's also timers. You can affect the timer values to be lower or higher depending on the situation. So you'll notice that when we transition from PBST to rapid, and I'm going to do that on 2 switches when I do it. I'll do like switch 1 and switch 2 will be like newer core switches, and we need to optimize their environment. You'll see some legacy connectivity. Rapid PBST and PBST are backwards compatible with each other. So rapid PBST needs to be backwards compatible with PBST because it's just enhancing the way that it does things, but it still has the same functionality. So I will make, you'll see and I forget what it looks like. It'll show up it should show up in the outputs, where because the timer values are the same, and you might have an older switch, you would end up having, I forget what the term is. It's been a while since I've seen it. But switch 2 will know that switch 4 is like legacy, and we'll see how that plays out. So what'll end up happening is, actually it's literally right here. It's actually bugging me that I don't know. So on switch 1, right? So if I was to type in here spanning tree mode rapid, and then do a show spanning tree for VLAN 1315, we should see, is it going to be on this side? I think it'll be on this side. There should be a trigger, or at least an output of something. There it goes. That's right. So it's a shared peer. But what basically just means it's STP. So this is telling me that it's STP. So it's telling me that it's spanning tree protocol. It's telling me that it's a legacy version of spanning tree. So if I was to look on this one here, this one's not going to show anything. But you can tell just by looking at it that it's telling me that it's a legacy switch. So you'll see that when you make the change and how that comes into play. So there's that. So by changing the mode, it lets the rest of the environment know what's going on. Then you get port fast. So port fast is how you transition from blocking directly into forwarding right away, and you don't have to deal with listening or learning. So you bypass that 30 seconds of downtime right away. BPDU guard is BPDU, bridge protocol data units, how a switch sends hellos to other switches. If I have a scenario where I have another switch attached to me and I start sending BPDUs on an interface that should not be used as an infrastructure interface, meaning I am expecting an endpoint like a PC to be plugged in, I shouldn't expect BPDUs to be received on that interface. So if I do receive a BPDU in on that interface, I'm immediately going to shut it down. And when you do that, you're taking the port down. So this potentially blocks any type of layer 2 loop that might be caused by something being plugged into itself. I've seen people accidentally run a cable from one switch to itself, from gig 1 to gig 12 by accident, and it blocks the port because it detects a BPDU. So it's not something you want to have happen, but if it does, it does. Now, BPDU filter still operates in the same mechanism, right? It prevents a switch from accidentally joining the network on an interface that is not supposed to be connected to on that port as a switch, like it's supposed to be an endpoint, but it filters out the BPDU. It like silently drops it. So, and I think it triggers a warning. We'll talk about that. We'll actually go through each one of these. Loop guard is detecting a loop, and then root guard is basically the locking down of a root bridge. You only want that particular switch to be your root. So that is essentially the capability here. Now, I know I've demoed out a few things in this video just because of the fact that it's like I wanted to show you what I meant. Because sometimes it's easier to see what I'm talking about than it is for you to have a loose understanding. So what I'm going to do is in the next video, I'm going to walk you through how to configure everything. It'll be a short section for spanning tree. I'm not going to spend a ton of time in any one of those topics because all the things that I'm showing you how to do are also things that you can read through here. And I'm going to do my best to try to remember to put all of these things, to put like a link in the description of the video so you can just reference it. And then we'll also talk about UDLD as well and how that comes into play and how that works, because it's something that you're going to definitely want to know about because it is called out. So I haven't talked about UDLD, so I'll talk about that in its own section probably when I talk about administration, because it's more about preventing loops on fiber pairs and stuff like that. Unidirectional link detection. So if you only have one path, the link is there, you'll take both of them down. So you're not blindly sending traffic and not receiving anything back. So we'll talk about that more in detail later on. But that is what I wanted to talk to you guys about this video, give you like a high level review of how these particular features work and that type of stuff. And then in the next video, I'll walk you through some basic configuration examples of how each one of those work. And then we'll pretty much be done with spanning tree. There's, like I said, I'm not going to go into the finite details, but I will go through and show you guys how to navigate and configure things and stuff like that. So it's not very difficult for you guys to follow through. And then in the video after that, once I get done with all those pieces, we'll start diving into ether channels, and we'll talk about how that comes into play and all that good stuff that goes along with that. So if you guys have any questions for me, do feel free to drop a comment in the comment section below. Questions, comments, feedback, whatever that might be. And if you haven't already done so, please like, share, and subscribe. And I'll catch all you fine people in the next video.